Welcome back to our channel. Today, we're exploring an incredible topic, the theoretical maximum temperature and the coldest temperature we can experience. While we all know that absolute zero is the coldest temperature possible, have you ever wondered what the hottest temperature in the universe might be? Strap in, because we're about to embark on a journey through the extremes of temperature. To kick things off, let's talk about what temperature actually is. Think of it as a measure of the average energy of particles. Picture a pot of water on the stove. As you heat it up, the water molecules start moving faster. That's temperature in action. So, what happens when we crank those temperatures up to the extremes? Let's consider the coldest temperature known to science, absolute zero, which is 0 kelvins, or about minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. Imagine a world where time stands still. At absolute zero, all matter comes to a grinding halt. Atomic motion ceases, and the laws of classical physics no longer apply. At this temperature, a world where nothing moves, not even the electrons. Scientists have come remarkably close to reaching absolute zero in laboratories, creating conditions so cold that atoms behave like a single quantum entity, exhibiting phenomena like Bose-Einstein condensates. It's a state of matter that sounds like science fiction, but is very real, where particles act in unison. Beck models have fascinated scientists since their prediction by Sachendranath Bose and Albert Einstein in the 1920s. The quest to produce a Bose and Einstein condensate in the laboratory was stimulated by a paper published in 1976 by two program directors at the National Science Foundation, William Stwally and Louis Nosanow, proposing to use spin-polarized atomic hydrogen to produce a gaseous BEC. This led to the immediate pursuit of the idea by four independent research groups. These were led by Isaac Silveira from University of Amsterdam, Walter Hardy from University of British Columbia, Thomas Greytak from Massachusetts Institute of Technology and David Lee from Cornell University. However, cooling atomic hydrogen turned out to be technically difficult, and Bose-Einstein condensation of atomic hydrogen was only realized in 1998. Today, researchers study this model to understand quantum mechanics' role in macroscopic systems and explore novel quantum computing applications. Now, let's journey to the core of our Sun, where temperatures soar to about 15 million kelvins, that's around 27 million degrees Fahrenheit. This intense heat comes from nuclear fusion, the process that powers stars. Imagine being in a place where nuclear reactions are constantly occurring. It's so hot that hydrogen atoms collide and fuse to form helium, releasing energy that lights up our solar system. But it doesn't stop there. In massive stars, temperatures can reach an astounding 500 million kelvins. Just before a supernova, an explosion that can outshine entire galaxies, the core temperature might spike to over 100 billion kelvins. Think about that, a single point in space becoming hotter than the surface of a star. Next, let's rewind to just after the Big Bang, when the universe was a dense soup of particles. At that moment, conditions were extreme. Using calculations of early universe, scientists estimate that at just 10 microseconds after the Big Bang, the average temperature soared to 3 trillion kelvins. That's hotter than the core of any star and similar to what we see in high-energy experiments at facilities like the Large Hadron Collider. Can you imagine being in a universe that hot? It was a place where quarks and gluons, the fundamental building blocks of matter, floated around freely, creating a chaotic and energetic environment, but that is still nothing. So, what about the theoretical maximum temperature? Enter the Planck temperature, which is approximately 10 to the power of 32 kelvins. This value emerges from the interplay of fundamental constants in physics, the gravitational constant, g, the speed of light, c, Planck's constant, h, and the Boltzmann constant, k. The Planck temperature represents a threshold beyond which our current understanding of physics breaks down. Imagine trying to comprehend a reality where the very fabric of space and time loses its meaning. At this extreme, energy levels are so high that it's theorized that quantum black holes could form. In essence, the laws of physics as we know them, derived from relativity and quantum mechanics, fail to apply at this temperature, leading to a regime where a unified theory of quantum gravity is required. As we traverse from the chilling depths of absolute zero to the blistering heights of the Planck temperature, we witness a universe that is both bewildering and awe-inspiring. Each extreme invites us to ponder the fundamental nature of reality itself. If you enjoyed this exploration of temperature extremes, give us a thumbs up and subscribe for more mind-bending scientific insights. What extreme phenomena would you like to explore next? Share your thoughts in the comments below, we'd love to hear from you.